Excuse, I'm just getting over a little bit of a respiratory thing too. So you've heard from several people, but excuse if you hear a little bit of scratchiness. So I'm going to focus, like Pete said, on some more of the geologic specific focus of this work. The idea here is to leverage machine learning models, the AUV data, the LiDAR data, the multi-beam data, bring all that, fuse all that together to get a regionally informed substrate map that's much more precise than anything currently out there. This is a true collaboration. So I'm at Michigan State University, but this is really truly a collaboration. Largely, I've been working with Pete on this, but there's other collaborators certainly in the project. I've also been collaborating closely with the partners at NOAA, Brandon Crumwoody and others, on developing the seamless bathymetric DMs that you'll see here. So oftentimes what we think of when we think of data density, we see these nice, beautiful maps of the lake bed and even including geologic maps that, okay, we expect to see fine sediment here and coarse sediment there. But in reality, we know the data density is otherwise. And a lot of this data is perhaps not the most up-to-date, as I'll show you in a minute here, but it's really important that we have the most up-to-date and informed maps for species management and habitat management, such as whitefish and round goby, for a couple different reasons. Now, Pete and his group have been really great about identifying and distributing data sets for training machine learning models to identify everything from rocks, which is what we're working on currently, to submerged aquatic vegetation, round goby, and others. So it's kind of an ecosystem, if you will, of technology to try to get a more comprehensive lake bed habitat map. If we dial in on the geologic maps, what we see is something that looks like on the left here, where the data sources really go back to the foundational data sources for a lot of our geologic understanding of Lake Michigan, the lake bed, go back to the 1960s, 70s, and 80s. There are some newer data sets within that, and Illinois is kind of an anomaly in that sense. They focused a little bit more on it to their 100% their credit. But still, these data sets are pretty out of date and pretty sparse in terms of data, the methods and the distribution of data points. When you look at what the actual classes are, you get a high degree of variability, excuse me, across these different data sources, which leads to bedrock with a capital B, bedrock without capital B, bedrock algae, all these different data sources, which you can combine to what we see on the right and kind of simplify that. But again, remember that's based on largely data sources that go back 1960s, 1980s. So there's a really important need to update these maps. Pete talked about it a little bit in terms of being able to extrapolate round goby numbers, also manage habitats and identify reefs as potentially important spawning habitats. So what we're going to use here is we're going to use a combination of that AUV with LiDAR and multi-beam data to really get at a machine learning informed approach to this. The foundation of these geologic substrate classifications does come from the AUV data. So the USGS has collected close to a petabyte of data, that's point clouds and images of the lake bed since 2019. And the goal here is to accurately characterize the habitat comprehensively. These images is what I'm going to focus on primarily. The color images are at, like Pete said, a fraction of a millimeter in terms of the actual spatial resolution. We then manually classified, and that's what I'm going to focus on right now, is the manually classified images into their dominant cover type, their dominant substrate type. So you'll see the 9 classes on the right here. For simplicity's sake, I'm going to focus in on aggregating them to coarse versus fine. The model becomes much simpler and much more accurate if we do that, although we are working on improving the granularity, if you will, of the models. So these AUV images, again, like Pete showed, are collected all across the Great Lakes. This is the subset of images that we're going to use for this. That's just over 5,000 images that we manually classified between 3 people, and then we had an arbitration process to come to some sort of agreement. And they're, again, in these 9 classes, which we're going to simplify to coarse and fine, so kind of a binary. We're going to then intersect those with a DEM, with the elevation model of the lake bed. This is what if you would go to the lake level viewer of NOAA, what you would currently see. The extent rimming the lake itself is going to have an elevation. We don't really have much in the middle. And this is at 3 meters. What if we can take and then expand that fusing the LiDAR with multi-beam data? And this is going to come into play later on when we actually intersect these. So what we could see is a huge increase in the coverage when we actually bring those new data sets in. There's over 175 different sources. So it's not a small task working with NOAA to try to find all these different data sets, some unpublished, some yet to be published, but actively being QA/QC'd. And we can fuse them into, instead of a 3-meter resolution, because the data density of the raw data has improved, we're going to refine that down to a 2-meter resolution DEM. So the ability then to resolve individual areas is much greater as you increase the spatial resolution. We then intersected these points everywhere where we had a geologic classification point with a raster, and then we train a machine learning model to say, okay, we know this is the classification here. Can you actually predict out elsewhere in the map areas where we don't necessarily have ground truth data? And what we get is a map that looks like on the right here, where your coarse are in your kind of magenta hues, your fine are going to be in your orange hues. And then there is a little bit of caveat here, sandbars, because they have a surface expression that's going to appear coarse, kind of linear features, but very prominent linear features. We actually had to pull them out as their own class. And I'll show you some examples of why that is and what it looks like in the next couple of slides here. The confusion matrix on the top right is important to look at. What we see is that the coarse tends to be about 74% accurate, but it tends to get mostly confused with sandbar. Again, why we pull out sandbar as its own class, because we know that it's composed of fine sediments formed by oscillating wave action. But we're getting about 90% accuracy with the fine as itself. We, again, in the receiver operating curve on the right, do see that the coarse doesn't perform quite as well as the fine and the sandbar, but it still performs reasonably well in terms of false positives. So I'm going to pop around to a couple different areas here. First, focusing on the west side of the lake. So this is an area that's pretty mixed in terms of the sediment. There was a large campaign to actually collect more data here within the last year or two. But I'm going to focus on, you can see there's a high degree of heterogeneity across the lakescape here. The center image is going to be the AUV images themselves. So you're kind of, again, sticking with the same color scheme. So your oranges are going to be your fine, and your coarse are going to be your magenta hues. We can see that we have some AUV training data in here, which is nice because then we can compare the output of that random forest, that machine learning model on the right here, to the AUV data that we have in that location. We can see a strong degree of agreement between those two. So areas where we would expect to see fine, like we see in the AUV images, are actually being classified accurately in the substrate model. Popping across to the east side of the state, this is an important one to look at. Although we don't have coarse and fine here, if we're looking at sandbars specifically, these long linear features that kind of ring the coast in certain areas are pulled out here very, very well, where we do have training data set like what we see in the middle here. It's important to note the sandbar training data sets were manually identified by myself and one other, just kind of through manually clicking out along the coast because they are so prominent in the elevation model. But then when we use those and examine how the random forest model predicts, what we see is that the random forest model predicts very, very accurately, very appropriately, these kind of bathtub rings, if you will, of sandbar classes. So the nice thing there is we're not conflating coarse substrates in the near shore with actually sandy substrates. And then this last area I find absolutely fascinating. It's an area we don't have any ground truth data, primarily because the area between Hog and Garden Islands here, just northeast of Beaver Island, is so shallow. So to put an AUV in there in the water, or an ROV, or bring a vessel in there, gets tossed around by the waves. There's clearance issues, there's all these challenges. So it's important that we can accurately characterize these areas, which are potential important areas for fish habitat, without having to do an extensive ground truthing effort there. All right. So the advantages of this random forest approach are first that it's very scalable across large regions. It's transferable to areas with similar geomorphology, although there's potentially challenges with Lake Superior, Lake Huron with different geologic settings, and that's one thing that we're working on. I'll talk about in a minute. You can adapt this to a wide variety of inputs and class distributions too. So I presented the coarse versus fine, but we're also working on 5, 6, and more class models as well. So I think our ability to do that will improve as we address some of these imbalance issues. And then one of the continued challenges with anything is the water clarity. Quite simply, if you can't see the bottom, we can't develop a ground truth for that location, and we can't use it. Similarly, if the water is not terribly clear, LiDAR has challenges and other issues too. Okay. Some of the future opportunities that we're working on are refining the models with new data. So as Pete mentioned, we continue to collect data collectively as a group. And then we're always trying to bring in new data and trying to increase the amount of training data that we have. We're also bringing in new data sets, LiDAR and multi-beam, actively, and we have a fused pipeline that we can then plug those in and produce a new surface very, very efficiently by comparison to a lot of manual approaches. We are working on augmenting the training data sets instead of using only the manually classified geologic substrate images, but also running those through the model like what Pete showed earlier and classifying those using machine learning model, and then using that classifications as further input to this random forest model for lakescape prediction. We do have issues with the model. I'm not going to pretend it's perfect. We have a lack of bedrock images for a couple different reasons. One is that's just where sampling has or has not been in the past for this data set, but we're working on improving that. And then also, we're not married to the model that we have right now. As new machine learning models and approaches, algorithms continue to evolve very, very rapidly, we continue to explore those approaches through work with Pete and his group and Angus that you'll see in a minute here and others. And then I should note the bottom one is really important. Eliminating or minimizing those mosaicing artifacts is something that has proved to be a challenge, especially when you're dealing with potentially LiDAR and multi-beam data sets that have anywhere from 8:1 to a half-meter resolution. So how do you seamlessly integrate those data sets in a way where you don't have these huge artifacts? Even a quarter-meter jump between data sets is not uncommon. So to focus in on the one particular area, it's really fascinating if you recall back to the original coverage of the kind of straits in the area between Beaver Island, the UP, and the Mackinac Island area. It was pretty sparse. When we add in the multi-beam data, we see there's a lot more heterogeneity in the landscape. We can actually identify glacial lineations that are deeper water than we ever expected. We can more truly better resolve the channel that runs under the straits and connected ancestral Lake Michigan and Lake Huron. And then more importantly, we can start to get a sense for, well, how does the geologic substrate vary across this area? And how really can that affect lake whitefish habitat and recruitment as well as other species? So it's really important that we have a more refined understanding of what the geologic substrates are in different regions for species-specific management, and we could do this more efficiently now. If we think back to the original AUV images, Pete kind of touched on it briefly. There is a high degree of overlap, sequential overlap between the sequential images. We could take those and we can run those through photogrammetry software to actually produce very, very high resolution elevation models and orthomosaics and even point clouds for those data. The really fascinating thing here is this is just one very small portion of the lake bed. It's actually on the Wisconsin coast. Apologies for not showing overview map, but the spatial resolution on this is sub-millimeter. You can identify individual shells in this, individual mussels, individual shells, individual objects. So our ability to do this in an automated pipeline is one thing that we're working on actively developing and furthering. The nice thing here is you could get a very detailed map of a reef potentially, or other area of interest. So there's ways that we can continue to expand this not only at the lakescape scale, but also at the very local reef scale. I'm going to show this visualization. This is a portion of the lake bed near Elk Rapids, so kind of up near Traverse City area. And this is in about 25 meters of water. So it's very, very shallow, very good light penetration naturally. And what we see here is as we go over this, this is showing the point cloud. You can see everything from sand ripples to shell hash to boulders to aquatic vegetation. So the nice thing is we have these very detailed data at a resolution of a fraction of a millimeter. And so then the challenge becomes, or the question becomes, well, it's great, we can get this pretty picture, but what can we do with it? And I'm not going to steal too much of Angus's thunder, but I just kind of want to introduce this concept of automating the detection and delineation of different features like invasive mussels, which is what we see on the right here where they've been identified in red. This is one of Angus Galloway's models that has been applied to this data set. You can actually even see a rusty crayfish in the upper right corner. He's only about yay big, but our ability to resolve these features is just incredible and opens up a plethora of opportunities for mapping. So thank you.